what we're gonna start with is qualitative analysis. Just to refresh your memory, that qualitative analysis really is the identification of an unknown substance. You're in the lab, you go to a crime scene, something like that. You find something which a powder, or you find some liquid, right? You don't know what it is. You take it back to the lab, you try and identify it. That is what qualitative analysis is about, identification of an unknown substance. Now, at this level, what you're expected to be able to do is identify cations and anions and gases. The gases that you're expected to identify are oxygen, carbon dioxide, hydrogen, sulfur dioxide, and nitrogen dioxide. Nitrogen dioxide is probably the easiest one to identify because it is a brown gas. As a matter of fact, whenever you see anything about brown gas being produced in qualitative analysis, it's usually going to be nitrogen dioxide. Okay. Carbon dioxide, as you know, extinguishes a flame. That's why carbon dioxide is used in fire extinguishers. It also turns lime water cloudy. Lime water is calcium hydroxide. So if you see a test being done with lime water and you see it turn cloudy, you know that carbon dioxide is present. Oxygen, of course, relights a glowing splint, and hydrogen would give a popping sound when you have a lit splint. Okay, so if you put a lit splint at the mouth of a tube and you hear a pop, you know hydrogen is present. Then now the anions that you need to identify for qualitative analysis here are the sulfate ion, sulfite ion, carbonate ion, nitrate ion, the halides, chlorine, bromine, and iodine, or bromide, iodide, and chloride, and well, we did say sulfate already, and so those are the anions that you need to identify. Nitrate is probably the easiest to identify because the nitrate ion, really, when you heat it, it produces a brown gas, which tells you that nitrogen dioxide is being produced. The only place you can get nitrogen dioxide from is from the nitrate ion. Nothing else will produce the nitrogen dioxide. Okay, so when you heat your solid and you get that brown gas, you know it's nitrogen dioxide, which comes from the nitrate ion. Carbonate, of course, you can react a carbonate with, well, for the carbonate, the sulfite and the sulfate, you're going to react those with a barium salt, and they'll form a white solid, and then you're going to react the white solid with acid. When you do that, what you're going to get is a reaction with the acid. When you react a carbonate with an acid, you would remember this from fourth form, that you get salt, water, and carbon dioxide. And then, of course, you can test the carbon dioxide being produced with lime water, and that will tell you that it is a carbonate. The only place you can get a carbonate from is from you can get carbon dioxide from is a carbonate. That's the only place you can get it from, nowhere else. For the sulfate now, SO42 minus, when you add that to an acid, you're going to get no reaction. No reaction occurs with the sulfate. So therefore, you know it's a sulfate. For the sulfite, you'll get a reaction, and what you'll see happening is that you see some bubbles being formed, and that bubble will be sulfur dioxide. Now, how do you test for sulfur dioxide? The first thing about sulfur dioxide is it has a choking odor. Okay, sulfur dioxide has a choking odor, and also it decolorizes litmus paper. So it is an acidic oxide. Acidic oxides are oxides that dissolve in water to form an acid. And these things are responsible for things like acid rain, right? So when you take sulfur dioxide and you add it to damp litmus paper, it's going to dissolve in the water in the litmus paper and form an acid. And so it is going to change the litmus paper to red. So sulfur dioxide will change litmus paper to red. The next thing now, so that's the sulfate, sulfide carbonates. nitrates. The halides now, what you do to test for your halides is you add silver nitrate solution. Now, when you react silver nitrate with a halide, you're going to get a solid. The solid may be white in the case of chloride, slightly yellow, cream in the case of bromide, and yellowish in the case of the iodide. Okay, so those three colors are what you'd use to distinguish them. But the thing about it is cream can look a little bit white. So therefore, you can then add some ammonia, which would distinguish all three of those things, which one you have specifically. And you could also add to that, adding them to sunlight, right? And when you add them to sunlight, it will change color in the sunlight, and then you will see really which one you have specifically. All right, so that is the essence for the nonmetals. For the cations now, so remember now, your qualitative analysis is the identification of a cation and an anion. That's what you're really trying to do. Okay, and so you're doing these tests to identify them. So once you have identified your anion, you can then move on to your cation. Right, the cations that you have to identify is quite a bit of them. So you have potassium, sodium, ammonium ion, calcium, well, calcium to a less extent, but still calcium, aluminum, lead, zinc, copper, iron. Basically, those ones are the ones that you have to identify. Now, the good thing about it is that your cations, some of them are colored. So when they're dissolved in water, they form colored solution. So copper 2 ions, for example, when they dissolve in water, they form a blue solution. And then iron 2, when it dissolves in water, it forms a pale green, yellowish green solution. It depends on how you see color. A yellow-green solution. Then now, iron 3, which is responsible for rust. And you know the color of rust is like brownish, something like that. So therefore, when you add iron 2 to iron 3 to water, it should give you a rust brown color. And that should tell you that you have iron 3. For the others now, they don't really form colored solutions. They don't really form colored solutions. Lead, though, on the other hand, when lead 2 ions react with iodine, you get a bright yellow precipitate. So every time you see that in qualitative analysis, and you know for sure. So if you add potassium iodide to a solution, you're going to see these things when we go through the question, right? If you add potassium iodide to a solution and the solution gets bright yellow, bright yellow, you know that lead is present in the substance. Okay, here we go. Right, so you know that lead is present in the substance. So this is basically a document that I use for qualitative analysis. Okay, and the steps that you take to identify your compound. Okay, that has to do with the solubility. Down here for this table, I'm just showing you basically the gases and what they can be produced from. For the most part, carbon dioxide will be produced from carbonate, not really hydrogen carbonate. We don't really tackle hydrogen carbonate as an anion. Then you have the thermal stability of the compounds in terms of if you heat them, what would they produce? Notice here that sodium and potassium over here, they are very stable. So heating them really doesn't do much. It doesn't really identify anything. And of course, you're testing for your cations. You add sodium hydroxide followed by a little bit of ammonia. Okay. So you add a sodium hydroxide dropwise, then you add some ammonia after that. So if you get a white precipitate, see there, if you add sodium hydroxide dropwise and you get a white precipitate, it could be calcium, aluminum, zinc, or lead. If the precipitate is insoluble in excess sodium hydroxide, so what you do is you take your test tube, right? You take your test tube, you add a few drops of sodium hydroxide. So that's your test tube. You add a few drops of sodium hydroxide to the sample. Then you shake it. You'll see a white precipitate form. So then you're going to see these white things at the bottom, right? And then you add a few more drops of the sodium hydroxide. Now, if the precipitate is insoluble, when you add the excess, it means that it is calcium. If the precipitate dissolves, then it means that it could be aluminum, lead, or zinc, one of those three. All right. Now, if it's a blue precipitate that you form when you add the sodium hydroxide, then you know it is copper. Copper form the blue ions. Remember I said, if you add excess and the precipitate is insoluble, it's still copper. It doesn't change that. If you get a dirty green precipitate, it's iron 2. If you get a rusty brown, it is iron 3. And of course, you're not going to get any precipitate with ammonia, with sodium hydroxide. But what you will get is, if you heat the solution, you will get ammonia evolving. Ammonia is the only common alkaline gas, which simply means that if it is alkaline, then when you add litmus paper to it, it will turn it blue. It is the only gas that you are going to interact with that will do that. Okay, so that's that. You can stop me at any time to just ask me questions if there's something you want me to clear up. Okay, so then now, you can then test with ammonia. The ammonia is just really to confirm. So let's say you do your first test with sodium hydroxide, and then now you want to confirm whether or not you have calcium, or you want to confirm aluminum, zinc, or lead, right? You do now your test with ammonia. It's the same procedure. You add the ammonia drop-wise, then you add it in excess. So when you add ammonia drop-wise, if you get no precipitate, PPT means precipitate, it means that that is calcium. If you get a white precipitate, it could be aluminum, lead, or zinc. If the precipitate is insoluble, it's aluminum or lead. If the precipitate is soluble, then it is zinc. So you can see how you are distinguishing the things as you go along. Of course, copper is going to form blue. Dirty green is going to be iron. And then your rusty brown is iron 3+. Okay, so confirmatory test now. If it is that you suspect that you have a certain cation, you can confirm its presence. So you will realize that this is the third test that you're doing for the cation. First, you added ammonia, sodium hydroxide, then you added ammonia, and now you're trying to confirm. If you want to confirm for lead, right, you add potassium iodide right here. It could be sodium iodide too, potassium iodide, it doesn't matter. The fact that you must have a solution of iodine ions, iodide ions. So you get a bright yellow precipitate. That's lead. If you add the potassium iodide and there's no precipitate, it means that it is aluminum. If you add dilute hydrochloric acid and you get white precipitate dissolves upon heating, that's also lead. No precipitate, it's aluminum. If you add potassium ion cyanate, which is this, they kind of cut this out now at CSEC level. You get a dark blue solution, precipitate rather, you know, it's iron 2. If you use this one now, this is iron 4, potassium 4, right? Hexacyanate now, you get iron 3. They kind of cut this out at CSEC level now. So they mostly do this at the CAPE level. So those are just a confirmatory test. All right. So let's get back to that document now to see what we can do. Okay, so what you should be seeing on the screen now is a
Past paper, sir.
past paper. That's what you're seeing, right?
Yes, sir.
Okay, it says in 2 separate experiments, iron metal and sodium bicarbonate. Let me see if they still do this. Were both treated with excess sulfuric acid. The results are both shown. The results complete the table. Okay. All right. So they treated iron metal and sodium bicarbonate with acid. Sodium bicarbonate is sodium hydrogen carbonate, as you can see there. Okay, so in experiment number 1, the solution turned pale green. All right, so you see, we just said if the solution turns pale green, it means that you have iron 2 plus ions. Sorry, okay? So that's what you need to write for your inference. Then it says a colorless gas evolves, splint goes off with a squeaky pop. Interesting. So what this means is that you are seeing that a colorless gas evolves and the splint goes off with a squeaky pop, which is an explosion. That tells you that hydrogen is being produced, right? Then now for the third one, it says a colorless gas evolved. It's a CO2 present. Of course, we could test for that, but they already gave that inference, so we don't need to do that. So that's what you would need to do for that table to get your marks. All right, so all we're doing really is just looking at the observations or looking at the inference and suggesting what would have caused that to happen. Okay, so let us proceed. It says state 2 physical properties of iron metal. Of course, iron is solid. That's a physical property, and it has a high density, high melting point, high boiling point. Okay, for this one, this is not really qualitative per se. This question, it's more thing there, metals and non-metals. So it says write a chemical equation for the reaction that occurred between iron metal and sulfuric acid. So of course, what you're gonna have happening here now, it should be pretty straightforward. Iron, which is a solid, plus sulfuric acid, H2SO4, which is aqueous, that produces iron 2 sulfate, which is aqueous, plus the hydrogen gas. That's why you got the popping sound. And you need to balance your equation. So that's 2, that's 2, that's 1, that's 1. So it's balanced. Okay, so that would be the equation that they're looking for there. That was in 2021, as you can see there. Right there, you can see when the exam was 2021. That was last year. So we proceed. So it says describe a test that can be used to confirm the identity of carbon dioxide in the experiment, include your expected observation. So the test that you can use is you can blow the bubbles on a lit splint, and if it extinguishes it, it is possibly carbon dioxide. But what your examiner really wants you to say is that you're going to bubble the carbon dioxide in lime water. So that would be the test. You bubble the gas in lime water, and your observation would be that the lime water turns cloudy. Okay. And then now write a balanced chemical equation, including state symbols for the complete reaction between sodium bicarbonate and sulfuric acid. So let us just do that as well. So what we have is sodium hydrogen carbonate, okay, which we could say is aqueous, or we could say it's a solid, depending. Sulfuric acid, which is aqueous, and that produces sodium sulfate and CO2 plus H2O. And of course, you now need to balance this. This is a liquid, this is gas. You then need to balance the equation, okay? So you can balance that. So we proceed now. Remember, Kimberly, are you still there?
Yes, sir.
You can stop me and ask me questions at any point in time. All right?
Yes, sir.
Okay, that's a different question. Okay, here's now another qualitative. We'll probably work about 5 of these and then we'll see how it goes, okay? Complete table 2 to show test carried out on solid doublet. No, the thing up here really is not that important. It's just what's down here. Let's see what this says now. A sample of solid doublet was moistened with sodium hydroxide solution, and I can't see what that is. Moist and red lemon blue litmus was held at the top of the test tube. It says ammonium ions present. So if ammonium ions are present and you test for ammonia, you're testing with sodium hydroxide. You know you're testing for cations with sodium hydroxide. So with ammonia now, with the ammonium ion, you're not going to get any precipitate. Okay? No precipitate with sodium hydroxide. Well, why can't I find my page? Okay, here we go. Oh. Right, here we go. Okay, so you get no precipitate for that. So that's what you would have right there. No PPT. No PPT for that. Okay, it says to an aqueous solution of doubler, a few drops of acidified silver nitrate is added. Aqueous ammonia was then added. So now they're basically testing for the anion that is present. So it says a white precipitate form, precipitate dissolves in aqueous ammonia. So the fact that a white precipitate is formed should tell you that chloride ions are present. So what you put over here is chloride ions. Okay, and so we move on. It says to an aqueous solution of W as a solution containing barium ions was added. Barium ions is used to test for these three species over here: sulfite, sulfate, and carbonate. It says in the inference that they are present. Do you notice how they write their inference? They don't say sulfate, sulfite, and carbonate is present. They just put it. Write them down because you're basically saying those things are present. So if those things are present, what would you observe? It's actually white PPT. You'd see a white PPT, and PPT is perfectly acceptable for this thing over here. Okay, it says dilute hydrochloric acid was then added. So you add dilute hydrochloric acid to this solution. There's no observation, but they say sulfate is present. So if sulfate is present, equation for the reaction between barium ions and sulfate ions. If sulfate is present, then what you're going to get is no reaction, first of all. Okay, you're going to get no reaction. And then they want you to write the reaction between the barium and the sulfate ions. Basically, they're asking you to write the ionic equation. So it's Ba2 plus, which is aqueous, plus SO4 2 minus, which is also aqueous, to produce BaSO4, solid. Okay, that's what they're asking you to do there. You have to know how to interpret the question that they're asking you for. All right, so we proceed. That was 1998. That's a long time ago. Let me see this. Okay. All right, so a student conducted a number of tests on aqueous solution of P. Some of the observations inferences are given. To a solution of P, dilute nitric acid is added, followed by a few drops of silver nitrate. So I didn't mention anything about nitric acid, but basically you're adding the nitric acid to dissolve any solid. Okay, so that's all you're really doing to free up the ions. Now, notice here now they said that silver solution is added. Silver nitrate solution is then added. What's the purpose of silver nitrate solution? To test for halides. So it says no halide present. Basically, no chloride, bromide, or iodine, which means no halide. So what observation would that be? That would be no PPT. Okay, so no PPT because no halide is present. Then now it says further down here now, to a sample of solution P, a few drops of copper turnings are added, followed by conc sulfuric acid. Now, earlier I said that nitrate ions, if you heat them, you're going to get a brown gas, which is nitrogen dioxide. Another way you can test for the presence of nitrate ions is to use copper turnings and conc sulfuric acid, just as what they're doing here. Okay, now notice the observation. Brown fumes evolve, which turn moist blue litmus red. So what would cause that? No, I'm going to say this categorically. Once you see brown fumes, once you see that, it's only one thing, NO2. That's the only thing, not bromine as some people think. It's not going to happen for this at this level. All right, so it's nitrogen dioxide, which is a brown gas. It's also an acidic gas, and this comes from acids, bases, and salts. All right, so you have to remember these things. I remember acids, bases, and salts is one of those topics on the exam. So acidic gases dissolve in water to form acids, and acidic gases are usually oxides of nonmetals. All right, then it says down here now, to a sample of solution P, a few drops of acidified solution, aqueous potassium manganate solution are added. The potassium manganate solution changes from purple to colorless. Now, the problem with this is that a number of things can cause potassium manganate 7 solution to change from purple to colorless. So all you need to do right here, and they shouldn't give you incorrect, is that a reducing agent is present. Okay, which may be NO2, right? A number of things can do it. And that's why this question is probably not going to come again, because it's too vague. Are you still there?
Yes, sir.
Okay, when I'm not hearing, I'm wondering if I'm talking to myself. To a sample of solution P, aqueous sodium hydroxide, of course, sodium hydroxide is used to test for cations. It says a green precipitate forms. What would form a green precipitate with The precipitate is insoluble in excess sodium hydroxide. What would form a green precipitate with sodium hydroxide? Well, iron 2 ions would form a green precipitate with sodium hydroxide. Okay, so therefore, we did that. Where's our thing? So therefore, what you write for the first part of the inference is iron 2 plus. Then it says the precipitate is insoluble in excess sodium hydroxide. So, but then for that part, what they want from you is an ionic equation. See it right down here. Ionic equation required. So you need to write an ionic equation. So this is the part that sometimes throws students off. How do you write the ionic equation, and what do I write for the ionic equation? Well, first thing is this. Iron is present. And what did you add to something to get iron? Sodium hydroxide. Now, if you have added iron and you added sodium hydroxide to a species and you get iron and you're supposed to write an ionic equation, the only thing that can be formed from that is the metal, which is present. So it's iron hydroxide, FeOH2 solid. Okay, iron hydroxide. So if iron hydroxide is formed, because you know it's iron from up here and the OH comes from the sodium hydroxide, right? Then you must have iron 2 over here and you must have OH, aqueous. And since there are 2 hydroxides over here, you put a 2 there and you put, well, nothing there, aqueous. Okay, now let's hypothetically say that this question said a blue precipitate was formed, blue, right? If a blue precipitate is formed, then it would be copper 2. There you go, it would be copper 2. And then the precipitate would be insoluble in excess. So in this case now, instead of iron, we would have copper, right? So that's how you get your ionic equation. And it's pretty much just these two anyway, for this level. So we proceed. See if we can do 2 more. Then we press on. Here we go. A nice one. It says now a student conducts the following test on solution C and solution D. Okay, you don't even need to read that necessarily. So let's go. To a portion of solution C, aqueous sodium hydroxide is added dropwise until in excess and then heated. It says sodium, ammonium, potassium, and what you call this now? Ammonium, sodium, and potassium ions present. If that is the case, you would observe no precipitate being formed. Okay? You get no precipitate when you use sodium hydroxide with what you call this now, sodium, ammonium, and potassium. All right? So therefore, what you would put is no PPT. Then now it says, let me get my marker here, no PPT. Then now it says that sodium, it confirms ammonia. So something must be happening while you're getting ammonia. Now remember, ammonia, if you heat ammonia, NH, the ammonium ion, with sodium hydroxide, which is ammonium hydroxide, if you heat this species, you are going to get ammonia. Now, ammonia, so what you would not know that it is ammonia, but there's something special about ammonia. Ammonia is pungent. Okay, ammonia is pungent. What do we mean by pungent? Do you know what I mean by pungent?
Sir, I heard the term before, which I don't remember.
Okay, in common language, you would say stink. Okay, in science, we say pungent. So it's just the scientific word for pungent. So you'd say a pungent gas. So you'd say pungent gas. That's what you would put, because you don't know if it is ammonia for sure, but you know that something is going to be evolved and it's going to smell pungent. Gas is with 1 S. It says the gas evolved is tested with moist litmus, and it says that is confirmed. Remember I said ammonia is the only common alkaline gas. So if you test it with moist litmus, then you're going to say red litmus turns blue. Okay? That's what you would have here, because it is the only common alkaline gas. So the red litmus would turn blue because of that. Okay. And then that's that. So we press on with this. 3 marks. It says to another portion of solution S, nitric acid is added, followed by silver nitrate. Silver nitrate is used to test for halides. So it says chloride is present. So if chloride is present, right, what does that mean is present? White precipitate would be seen, white PPT. Okay, this is then followed by the addition of ammonia. So what would happen when you add ammonia to a white precipitate containing, well, what would happen to silver chloride? It's actually silver chloride. The PPT would dissolve. Okay, so you'd say PPT is soluble or the precipitate dissolves, one of those things. Okay, that's what you would put for that one, that the precipitate is soluble. Okay. Then now, let's see. Right. Yes. To a portion of solution D, aqueous sodium hydroxide is added until in excess. So now, you have no observations, but what you have are inferences. It says aluminum, lead, and zinc is present. So what would you observe? You would actually observe a white PPT. Okay, so you'd see a white PPT. And then now the second dot, you'll notice that there are 2 dots. So you have to add something for each dot. Okay, it is important that you remember that you have to add an observation or an inference for each dot. So now when you add the excess sodium hydroxide to the white precipitate, right, what you're going to get is that the precipitate is going to be insoluble. So you get your white precipitate, then now the precipitate is insoluble. PPT insol. That's all that's necessary. Okay, so you should be seeing on the screen something which says energetics worksheet, right?
Yes, sir.
All right, let's go through what I'll be doing is I'll be going through the notes first, so to speak, the content, and then we try and answer some questions. So what is energetics? Energetics is really the study of how much energy you can get from a reaction. All right. Now, why is this important? This is important because long time ago, scientists and people recognized that certain reactions produce energy. And you can use this energy to do something with it. You can use it to turn a turbine to generate electricity. You can use it to cook your food. You can use it to do some other things, to drive a car, for example. Okay, so the amount of energy you're getting from a reaction really is important. It is important that you understand that you can get energy from a reaction. Now, there are 2 types of reactions. The 2 types of reactions are, you have exothermic and you have endothermic. Okay, now students tend to mix these things up a lot. They'll say that exothermic means heat is given out and endothermic means that heat is taken in. That's not true. Here's the situation. Every single reaction that occurs, you must take in energy. So let's say I have X bonded to Y, right? And X is reacting with XY is reacting with CB to give, so XY plus CB to give, let's just say XB plus YC. Let's just say that, okay? Yes, there you go. Right, to give that, okay? Now, for this reaction to occur, this bond must be broken and this bond must be broken, and the bond between Y and C must be formed and the bond between X and B must be formed. Okay, now for you to break a bond, it requires energy. Think about it in real life. You have a best friend. If there's somebody who wants to break that bond between you and your best friend, they must put in a lot of energy to do it, unless that wasn't really your best friend. Okay, so energy must be placed into that bond breaking. So you must absorb energy to do that. Now, when bonds are being formed, it's always easy to form new bonds to some extent. Well, it's easy to form new bonds. Bond formation releases energy. So remember now, To break a bond, you absorb energy. To form a bond, you release energy. So every single reaction involves bond breaking and bond formation. So every reaction involves absorption of energy and release of energy. How do you determine if a reaction is endothermic or exothermic? If the reaction absorbs more energy than it releases, then the reaction is endothermic. If it absorbs more than released, it is endothermic. If the reaction releases more energy than it absorbs, then it is exothermic. Now, your examiner is not really going to test you on this sort of thing like that, just for you to know and understand that, okay? So the next part of this thing is, so you know that there are two types of reaction, exothermic and endothermic. Now, here is what we want to look at now. How do I represent an endothermic reaction and how do I represent an exothermic reaction? Now, there are two ways you can represent endo and exothermic reaction. Exo, endo. You can use an energy level diagram. An energy level diagram simply shows you the energy, relative energies of the reactants and products. So it is represented on a graph like this, okay? With your exothermic reaction, your products have less energy than your reactants. So you simply draw something like this. And that's R for reactants and that's P for products. Now, the difference between the products and the reactants is what we call the enthalpy, delta H. Okay, and that's negative because it's exothermic. Now, in the endothermic, it is the opposite. The products have more energy than the reactants. So what you would have is a graph which looks like this, and this is reactants and this is products. And the difference between these 2 points, the reactants and products, is the enthalpy, delta H, which is positive. Now, you may ask yourself the question, now, since you are doing this in school, is it positive energy and negative energy? There's no such thing as negative energy. Negative energy is a social construct to suggest that somebody is not positive, okay? Energy is just energy. So the thing is, to distinguish between an exothermic reaction and an endothermic reaction, you use a negative sign for the exo and use a positive sign for the endothermic. Okay, that's all. So this is your endothermic, your energy level diagram. The next way you can represent endo and exothermic reactions is to use an energy profile diagram. So energy profile. It's basically the same as the energy level.
So the level is different from the profile.
Yes, they're two different things. They're basically the same. It's just that with the profile, you involve this thing called the activation energy. What is the activation energy? The activation energy is the minimum amount of energy needed to start a reaction. Okay, the minimum amount of energy needed to start the reaction. So if you have ever struck a match, you know that if you don't strike the match, the tip of the match with the sulfur on it, it would never light. So the energy needed to light that matchstick is the strike that you do. That's the activation energy. Okay, so you still have your reactants here, you still have your products there, but then now the distance from here to here, up here, is what we call the activation energy, EA. All right, that's activation energy. Same thing for over here. You have your reactants and your products, and then your activation energy is from down here to up here. So that's your EA, activation energy. All right, and the difference between your reactants and products is still your delta H. So that is still delta H. From here to here is still your delta H. From here to here is still delta H. What is delta H? Let me tell you what that is now. If you were to measure the amount of energy produced in a reaction under standard conditions, standard conditions are conditions that scientists or chemists have decided that are standard conditions, if you understand what I'm saying. it's a, I don't know any other word to use for standard. These are protocol conditions, in other words. So if you're doing a reaction and you're calling it something, it must be done in these and in these circumstances, under these conditions, right? Which is usually 1 atmosphere, which is a unit of pressure. Do you do physics?
No, sir.
Okay, 1 atmosphere, 0 degrees Celsius, or 298 K, depending on whatever the case might be. All right, so those are standard conditions. If you measure the amount of energy produced from a reaction under standard conditions, we call it the enthalpy, and we give it the symbol delta H. I'm not even going to get into the theta part. Okay. 1 second, sorry. Sorry about that, Kimon. Are you still there? Okay, so the enthalpy really is the amount of energy you get from a reaction under these conditions. Now, there are 3 enthalpies. Sorry, before I even go there. So if your examiner asks you to represent a reaction using a graph, this is what they're asking you to do. Either they ask you for the level or the profile, and you need to know the difference. Now, every graph should have labeled axes. So what should be over here is energy. Where's my thing? On the y-axis, you should have energy. And on the x-axis, you can have reaction path. It doesn't matter. And it's the same thing for all 4 of them. Okay? Energy, but make sure energy is on the y-axis. It must be. Okay? And then you have reaction path right there. So this is the situation. Now, this is what they... Go ahead.
Can I have on the y-axis energy content?
Yeah, you can have energy content because it's the same thing as energy. Hello?
Yes, sir.
Oh, okay. All right. Yeah. So there are, I'm going to clear this now. There are a number of enthalpy changes that are studied at the CSEC level. So you have enthalpy, and all of them are enthalpy of. Enthalpy of neutralization is the first one, neutralization. Okay. And this is the enthalpy change which occurs when 1 mole of water is formed from a neutralization reaction. And you see, again, you have to know your previous chemistry. I tell my students all the time, your first day of chemistry, what you learn on the very first day of chemistry, you're going to need it on the last day of your chemistry class, because it is needed to answer a question on that last day. So neutralization is a reaction between an acid and a base. Acid plus base gives you salt and water. So that's why that is important. So you have enthalpy of neutralization, the energy change which occurs when 1 mole of water, and it's all of them is for 1 mole of a substance, when 1 mole of water is formed from a neutralization reaction. Then you have enthalpy of solution. Okay. Enthalpy of solution, the energy change which occurs when 1 mole of a solute dissolves to form 1 mole of solution, a 1 molar solution, really. Okay. Then now you have enthalpy of combustion. Enthalpy of combustion, the energy change, they don't really test combustion at CSEC level. I remember they gave a question 1 year and they should not have done it. I think they had to give the marks for that, but they don't really test it and they say we shouldn't do it. But anyway, we still have to do it because CX is very strange. So the enthalpy of combustion is the energy change which occurs when 1 mole, remember all of them is 1 mole, when 1 mole of a substance burns completely in oxygen. Okay, so that's enthalpy of combustion, neutralization, and solution. So now that you know that, now that you know that, we can move on. All right. So let's get back to this thing now. Select. So let me see now. I'm not gonna do that. It's too dark. Okay. Not seeing this. All right, let's answer this. Let's start here. It's very obscure. Can't see that. Let's start here. You should be able to see this, right? Oops. You can see it?
Yes, sir.
All right. It says when a small piece of calcium is added to water in a beaker, a reaction occurs. What would you observe? First of all, if you add water to sodium, if you add calcium to water, that's 2 marks. You would observe that the calcium would react with the water to form calcium hydroxide. So calcium, which is a solid, plus the H2O is going to give you calcium hydroxide and hydrogen gas, H2 gas. Aqueous. So what would you observe? You'd observe effervescence. You know what effervescence is?
Yes, sir, but I don't remember the definition.
Okay. You remember what I said pungent means?
Yes, sir.
What did I say it means?
Sir, you said it means a scent that is not smelling good.
Okay, you can say stinking, it's acceptable. When we say effervescence, we mean bubbles. So you would say bubbles, we say effervescence. See, effervescence sounds like you're smarter, but it's just bubbles, really. Okay, so you'd observe bubbles and you can write the equation to get the 2 marks because it's 2 marks. They're not going to give you 2 marks for nothing, I can tell you that. Okay, so the next thing now it says, the next thing now it says, see, that's the thing. It says 50 centimeters cube of water was heated from 20 degrees Celsius to 25 degrees Celsius in the reaction. Calculate the energy given off. All right, so now to do this, it says you have to calculate the energy. So EH, you're going to use the equation EH is equal to MC delta T. EH is equal to MC delta T. Let's define these things now. M is the mass of the water. But you're saying to yourself, they didn't give us a mass of water, they gave us a volume of water. Well, the density of water is 1 gram per 1 centimeters cube, which really means that if you have 1 centimeter cube of water, you really have 1 gram of water. If you have 1,000 centimeters cube of water, you really have 1,000 grams of water. So if it is that you have 50 centimeters cube of water here, you really have 50 grams of water. So we can put 50 grams right there, times the specific heat capacity of water, which is C. The specific, you don't do physics, but the specific heat capacity of water just simply means how much heat that is needed to be added to water before the temperature changes by 1 degree Celsius. But we're not going to get into that. Suffice to say that the specific heat capacity of water is 4.2 joules per gram per Kelvin. Okay? Kelvin is the SI unit of temperature. In other words, scientists have agreed the units to measure certain things in. And to measure temperature, it's kelvins, not degrees Celsius or Fahrenheit. All right. Then now the temperature change. Delta T. Delta means change. It means T2 minus T1, which really means the big temperature minus the small temperature. Okay. So here it is 5 kelvins. Even though it gives you in degrees Celsius, it's still kelvins. It's still kelvins because if you move from 10 degrees Celsius to 20 degrees Celsius, the temperature changes 10 degrees. If I move from 10 kelvins to 20 kelvins, the temperature change is still 10. Okay, so then kelvins cancel there, grams cancel grams over here, and then you can do your multiplication. You have a calculator with you, right?
No, sir. I can use my phone.
What's that?
No, sir, but I can use my phone. I don't have a calculator, you know.
You can't use your phone, you know, times 4.2 times 5. So that works out to be 1050. 1050 joules. All right. Don't trust your phone with these calculations. All right. So that's it. So basically, we would have gotten 1050 joules from this reaction based on the calculation. EH is equal to MC delta T. The next question says, is the reaction endothermic or exothermic? I want to hear what you think first. Do you think it's endothermic or exothermic?
Sir, endothermic, sir.
You think it's endothermic? All right. Unfortunately, you are incorrect. Now, the easiest way to determine if the reaction is endo or exothermic, look at the temperature change. Okay? If the temperature increases, it is exothermic. If the temperature decreases, it is endothermic. Okay?
Yes, sir.
And that's it. So the temperature moved from 20 to 25, exothermic. Now, it says write the equation symbols for the reaction between calcium and water. We did that already. So we press on. Next thing. All right, so here's another question, which is a lot better for us now. Trying to zoom in here. Okay, so it says when 100 centimeters cube of 1 molar nitric acid was added to 100 centimeters cube of 1 molar sodium hydroxide in an insulated cup, the temperature rose from 27 degrees Celsius to 33.9 degrees Celsius. Is this endo or exo?
Miss, sorry, sir, this is exothermic.
Exothermic, right? Because the temperature rose. So the first thing they ask you for is to write a balance equation to show the reaction between nitric acid and sodium hydroxide. So we write an equation. Nitric acid is HNO3. You have to remember these things. You know, all acids are aqueous. All right. Sodium hydroxide is also aqueous, NaOH, aqueous, and that produces sodium nitrate, NaNO3, which is aqueous, plus water. Acid plus base gives you salt and water. So that's your equation right there. Okay. The mole ratio is 1 to 1 to 1 to 1. All right, so that's our equation. We have to clear that because we need the space. It says how many moles of sodium hydroxide are there in 100 centimeters cube of 1 molar solution. Now, mole concept is a part of the 12 topics that they use, but mole concept is an application of information and not necessarily what we would you say now, a topic in itself. I hope I'm getting across to you clearly. In other words, testing of moles by itself is not something that CXE does normally. They may do it, but it's not something they do normally, okay? Because you need mole concept to answer questions about energetics. You need it to answer questions about titrations, rates of reactions, even organic chemistry, okay? So it is not something that they usually test by itself. They test it in application of other things. So this right here is a mole concept question because it says right there, how many moles? How many moles? So we're trying to find the moles. You must have done titrations. I'm going to explain what this means though. 1 molar or 1 mole per dm cube. What that means is that I have 1 mole of the substance in 1,000 centimeters cube of solution. You may say to yourself, now, where did I get 1,000 centimeters cube from? Because you don't see that up here. What you see is dm cube. Well, it turns out that 1 dm cube is equal to 1,000 centimeters cube. All right. So that's where that 1,000 centimeters cube comes from. And it says 1 mole per dm cube. 1 mole per dm cube. So it means that for every dm cube, you have 1 mole. In other words, in every 1,000 centimeters cube, you have 1 mole. And that's why I can write this statement, 1 mole is equal to 1,000 centimeters cube. The question now is asking us how many moles are there in 100 centimeters cube. So the question is, if I have 1 mole in 1,000 centimeters cube, how many moles? X, since I don't know, I'm going to call it X. X moles is equal to 100 centimeters cube. Then now you need to cross multiply. Okay? You do this in math. So you cross multiply. So when you cross multiply, you're going to end up with 1,100 divided by 1,000. I'm just going to clear it to get the space. So you're going to end up with 100 divided by 1,000. And that's easy math now, right? That's 1 divided by 10, which is equal to 0.1 moles. Okay, so that's our answer. You will also notice that it's the same amount of nitric acid that it is for sodium hydroxide. So that calculation would be the same thing for this down here. Okay?
Yes, sir.
Okay, dokes. So now we press on. It says, how many moles of sodium nitrate were produced in the above reaction? Now, here's the situation. We did write the equation, and I'm just going to shorten the acid as H plus, shorten the acid to make it H plus, and the hydroxide to make it OH, the base sodium hydroxide, to give the water plus the sodium nitrate. Okay? So they're asking now how many moles of sodium nitrate were produced. Well, we know from this equation that I've just written that 1 mole of that reacts with 1 mole of that to give 1 mole of that to give 1 mole of that. No, we just calculated that we have 0.1 moles of that and 0.1 moles of that. So if 1 mole gives 1 mole, reacts with 1 mole to give 1 mole and 1 mole, and I have 0.1 moles, then I'm going to get 0.1 moles to 0.1 moles. Okay, since it's 1 to 1 to 1 to 1. So that is where what you do for that bit there. Okay, then now it says calculate the heat evolved in the experiment. When you're calculating the heat evolved, what you need to do is use the equation EH is equal to MC delta T. EH is equal to MC delta T. So the question now is, what is the mass of the solution? So let me go back up. What's the mass of the solution? What's the total volume of the solution based on this question?
100 centimeters.
100, that's what you said?
Yes, sir.
Okay, but It's 100 for nitric acid, right?
Yes, sir.
And 100 for sodium hydroxide. So when you put both of those together, how much would you get?
200.
200. So the mass of the combined mass of the solution is 200 centimeters cube. So that basically works out to be 200 grams. Okay. So for your EH is equal to MC delta T, your mass is going to be 200 grams times the specific heat capacity of water, which is 4.2 joules per gram per Kelvin. That does not change, by the way. Okay. Times the temperature change. It moves from 27 degrees Celsius to 33.9. So that's 6.9 kelvins. Okay, cancel that, that cancels that, that cancels that, that cancels that. You must include units in your calculation, because if you don't, you're going to lose marks. All right. And that works out to be 5796 joules. Okay, so that is the heat energy produced in this reaction. That's the heat energy evolved in this reaction, which would be right there. The next question now says, what is the heat produced when 1 mole of nitric acid reacts with 1 mole of sodium hydroxide? In this question, 0.5 moles of nitric acid reacted with 0.5 moles of sodium hydroxide, producing 5,796 joules. So what we can write is 0.1 moles produced 5,796 joules. They're now asking you, okay, if 0.1 produced 5,796, how much would 1 mole produce? And that's X. Then you cross multiply. When you cross multiply, you're going to recognize that you would end up with X is equal to 5,796 joules times 1 mole divided by 0.1. And that works out to be basically 57,960 joules. Now, the situation now is this. Your examiner wants you to convert this to kilojoules. So all you need to do is just simply move your decimal point 3 places to the left, and you end up with 57.96 kilojoules per mole. Okay. Now, because the reaction is exothermic, you can just put a minus sign right there. All right. And that's what your examiner is really looking for. Okay. Yes.
Yes, sir, I'm following.
Okay. Now look at question 2. It says the heat of combustion of methanol is given as 640 kilojoules per mole, which means that for every mole of methanol, 640 kilojoules is released. They're now asking you, determine the heat released when 8 grams of methanol are burnt in oxygen. This is pretty straightforward if you look at it. All right. So you first need to convert the 8 grams of methanol to moles. Moles is equal to mass divided by molar mass. The mass is 8 grams. The molar mass of methanol is given in the question, 32. So that's 8 divided by 32, which is 0.25 moles. All right, so that's the answer. We have basically converted 8 grams to moles. It's the same thing. 8 grams is equivalent to 0.25 moles. They're saying 1 mole of methanol produces 600. 1 mole is equal to 640 kilojoules. Kilo means times 10 to the 3 joules. So how much would 0.25 moles produce? That's what they're really asking you. So all you need to now do is multiply 640 times 0.25. And that is going to work out to be 160 kilojoules. Okay, so it would be X, of course. And then you cross multiply and you get 160,000 kilojoules. So this question is not too bad when you look at it. It's just reasoning it out. That's what mole concept is about, reasoning things out. Okay? I want to get to an actual CXC question. Well, this is one. This is an actual CXC question now. Let me see. When chemical reactions occur, heat may be given off or taken in from the environment. What changes occur during a reaction that account for this fact? This is an actual CXC question. This is interesting. Let me see when they gave this. This was in 2005. They probably don't give this again. So anyway, remember I mentioned this already, that they're really asking you, why is it reactions taking energy and why they give out energy? Remember, energy is taken into break bonds, energy is released when bonds are formed. Full stop, full 3 marks. Trust me on that. You simply say energy is taken into break bonds and energy is released when bonds are formed. They have to give you the full 3 marks. Okay, because you have spoken about everything. Then they'll now say define the term heat of neutralization. Heat of neutralization is the energy change which occurs when 1 mole of water is formed from a neutralization reaction. If you don't want to use back the word neutralization, you say the energy change which occurs when 1 mole of water is formed from the reaction between an acid and a base. Okay? Next question. The next question now says, it is strong base, such as sodium hydroxide, or that the heat of neutralization is the same. They're now saying account for this observation. The reason for that is simple. When you react the acid and the base, because they're completely ionized, they combine together to form 1 mole of water. That's one thing. The next thing is that it is done under standard conditions. Okay? They won't ask you this though. It's 2005. All right, so here's another question. This should be actual. This is 2005 again. It says when 12 grams, when 12 grams of potassium nitrate is dissolved in 100 centimeters cube of water, the temperature drops by 4.2 degrees Celsius. Is this endothermic or exothermic?
Exothermic.
It's what?
Exothermic, sir.
What happened to the temperature? Did the temperature rise or did it fall?
Sir.
It what?
It decreases.
It decreases. So what did I say? If the temperature falls, what type of reaction is it?
Thermic.
I said what?
When it decreases, it's endothermic.
Right, it's endothermic. You keep breaking up when you say the word. Okay, so it is endothermic. So it says here now, using the above information, calculate each of the following. The number of moles of potassium nitrate used in the experiment. Moles is equal to mass divided by molar mass. It was 12 grams, so it's going to be 12 divided by potassium, which is 39, plus nitrogen, which is 14, plus oxygen, which is 16, but there are 3 oxygens, so that's 3 times 16, which is 48, and that works out to be 101. So it's 12 divided by 101. So 12 divided by 101, that works out to be 0.118. 0.1188 or 89. Okay, moles. So this is your mole concept here coming in. The heat change for the reaction. So you're now supposed to calculate the heat change for the reaction. How do you do that again? EH is equal to MC delta T. So EH is equal to MC delta T. M is the mass of the water. So let's go back up and see how much water was used. 100 centimeters cube of water. So we say now that's now going to be equal to 100, right? Times 4.2. Remember, it's always that, and include your units, times the change in temperature, which was 4.2, because they didn't really give that one. So it's going to be 100 times 4.2 times 4.2. Interesting. So that is 1764 joules. And that's how you get your answer there. Now, I'm sure they're going to ask us now to calculate the enthalpy of solution, as usual. See, the enthalpy change in the kilojoules per mole. So that's what they're now asking. So all you now need to do is divide the answer you get for the heat change by the number of moles. Divide the answer you get in the heat change by the number of moles. So what that would be now would be the enthalpy delta H would be equal to 1764 joules divided by 0.1189. Give me a second. Right. So when we do this division, what we end up with is 14. We end up with 14,835. 14,835.996, which is still 14,836. Now they want their answer in kilojoules per mole. So what you need to do is move the decimal point 3 places and you end up with 14.84 kilojoules per mole, right? This reaction is endothermic, so you put a plus sign there. And then that's that. Okay? So that's what, then no, say no. So that would be the answer for that. State one assumption you made in your calculation. Now, there are a number of assumptions that you are making. The very first one is that the mass of the solution, when you remember when you calculated the heat change, you use EH is equal to MC delta T, and we use the mass of the water as the mass of the solution. Now, we are assuming that the density of the solution is the same thing as the density of pure water. It's an assumption. All right, so that's one assumption. We're also assuming that the specific heat capacity of water is the specific heat capacity of the solution. These are not necessarily true. We're also assuming that there is no heat loss. Remember now, for you to measure the temperature change, you must use a thermometer. So therefore, you are assuming that the thermometer is detecting every bit of temperature produced in the reaction. That's not going to happen for sure. Okay, so you are assuming that there's no heat loss. The reaction occurs under constant pressure, that the specific heat capacity of the solution is the specific heat capacity of water, and that the density of the water is the density of the solution. So these are the things that we're assuming. Is not 10:30. Okay. Final thing now is to draw a labeled energy profile diagram to represent the enthalpy change for the reaction. Notice here, Kimon.
Sir?
Okay, I'm just checking if you're there. Notice here they're asking you for an energy profile diagram. So you now need to draw the right one and the right one for the type of reaction. The reaction is endothermic. So therefore, the products have more energy than the reactants. And the profile diagram involves the activation energy. Okay, so then you're going to put your P there, you're going to put your R there, you're going to put energy over here, you're going to put reaction path there, right? You're going to then put in your delta, your positive 14.8 kilojoules per mole. You need to put that in, okay? And then you put in your activation energy, which is from here to here, EA. You need all of that to get your 3 marks, okay?
Yes,
So,
sir.
all right. Hey, you have to talk to me sometime because I don't know if I'm just talking to myself. Okay. So here's another question. Pretty much the same things again. We did this already, right? You have the concentration of the sodium hydroxide, you have the concentration of the hydrochloric acid. It's done in a styrofoam cup, so you need to simply calculate the heat of neutralization. In this question, though, they're very not nice to you. This was a while back, clearly. They didn't tell you what to calculate. They just simply said calculate, and you would need to know what to calculate. So the first thing you need to do is find the number of moles, and then after you find the number of moles, you would find the energy for the reaction, see, using the information. So you're going to use EH is equal to MC delta T to calculate the energy in the reaction. Then you're going to calculate the enthalpy of the reaction. And notice they're also asking you to calculate draw the energy profile diagram. This energy profile diagram is going to be exothermic. I can guarantee it's exothermic, and let's show you why it is exothermic. Because the temperature is going to rise. See there? On mixing, the temperature rises to 38.9. So we know it is exothermic. Okay? Any questions?
Yes, sir. I have a question.
Yes, please elaborate.
Sir, it is temperature 2 minus temperature 1, right, sir?
All right, so don't think about it like that. Just get the difference between them and know that you never have negative temperature. Okay?
Yes,
So
sir.
doesn't matter if they decrease or increase, just simply subtract them, but do not put negative degrees, the kelvins in your calculation. It's a temperature change. That's what it is. It's just moving from one temperature to the other. Okay?
Okay, sir.
All right. So that's that. So the next bit now is